Hey guys, hello everyone. Very welcome to Rasayan Academy, all of you. So in this particular video, we are going to be discussing about a very important topic, that is kinetic isotope effect. And as you know, it has been recently very popularly asked in your CSIR net examination, in the GATE examination. It has recently become very popular. You are getting questions, previous year questions, you'll see in the exam. So what we are trying to do is, this is a very short video which is going to discuss kinetic isotope effect, both the primary and the secondary effects, and also we'll try to see some important examples. Okay, you can check out the previous year questions after this as well. All right, so yeah, let's start. So guys, what is a kinetic isotope effect? Kinetic isotope effects are the changes in the rate observed when a proton or a hydrogen atom is replaced by a deuterium atom in the same reaction. All right. So, when we are talking about same reaction, it's not that we are talking about two different reactions. So, within the same reaction, if let's say there is a carbon hydrogen bond and I'm substituting it with a deuterium, what is going to be the change in rate of reaction? If there is any change, then we say there is a kinetic isotope effect. So for any reaction, kinetic isotope effect is defined as the ratio of rate constant when substrate contains a proton with the rate constant when the substrate contains a deuterium atom. All right. Now, why there is this different? Why do we have the kinetic isotope effect? Let's talk about this first of all. So you see this graph on the screen. All right, this is going to explain a lot of these things, that why the effect is present at the first place. See, there is always a difference in a carbon hydrogen bond breaking. All right, why? Because the inherent energy of a carbon hydrogen bond, that we call as a 0 point energy. Okay, what is the 0 point energy? We know that every molecule, even if it is frozen at very low temperature, it will still have some vibrational energy, and that is known as the 0 point energy. All right. So the 0 point energy for a carbon hydrogen bond is higher than a carbon deuterium bond because of more vibrations, or because of easy vibrations due to less reduced mass of carbon and hydrogen as compared to carbon and deuterium. ठीक है, तो ड्यूट्रियम का मास बड़ा रहता है, इसीलिए ड्यूट्रियम का और कार्बन का वाइब्रेशन जो है, इट इज लेस as compared to carbon hydrogen, so hence higher energy for this. Now what happens is, when we are trying to break that bond, so it must reach some dissociation energy. So when it reaches this dissociation energy, when we want to break the carbon hydrogen or the carbon deuterium bond, this energy must be reached, which is over here, shown by this line. Now you see the difference of a carbon deuterium bond is greater, because CD का energy lower था, इसीलिए इसका difference ज़्यादा है, greater difference, and the CH energy was higher, that's why the difference is lower. So the delta G, the free energy which is required for bond dissociation, is lower for the CH bond, that's why it breaks easily. Okay, so the 0 point energy of the carbon hydrogen bond is higher than the carbon deuterium bond. Then as a result of this, we say that this is going to be making the CH bond easy to break as compared to a CD bond. All right, now we always see the kinetic isotope effect if the carbon hydrogen bond breaking is necessarily breaking in the rate determining step. So take care of this. It's a very important point, guys. You have to remember this, that the bond breaking must be in the rate determining step. All right, that is going to give you a primary kinetic isotope effect, because when it is involved in the rate determining step, so it is affected directly. All right, so the carbon hydrogen bond breaking is affecting the rate directly. So a primary kinetic isotope effect will be observed when the difference, the KH upon KD difference, maximum is 7 and minimum is somewhat around 2, greater than 2. ओके, सो मैक्सिमम 7 मतलब कि इसका रेट बहुत जो रेट में डिफरेंस है, रेट कांस्टेंट में डिफरेंस है, वो ज्यादा से ज्यादा 7 हो और कम से कम 2 हो. ठीक है, KH upon KD, this ratio, then we see a primary kinetic isotope effect. We will also see examples. अभी हमने सिर्फ रीजन कंसिडर किया है. ओके, So as we said guys, that primary kinetic isotope effect will only be observed when we see the carbon hydrogen bond breaking in the rate determining step. Lekin let's say if it is not present in the rate determining step, are we still going to get the isotope effect? Let's see for which example it happens. So isotope effect may also be observed when the substituted hydrogen atom is not directly involved in the reaction, such that such effects known as secondary kinetic isotope effects are smaller than primary effects and are usually in the range of Kh upon Kd is equals to 0.7 to 1.5. ये अगर इस के अंदर, let's say इस ratio के अंदर आपका if the kinetic isotope effect is existing, then we say it is secondary, because primary is very high because the rate determining step involves the CH bond breaking. Secondary is a bit lower. Okay, so when do we observe this? They may be normal secondary kinetic isotope effect like this, where Kh upon Kd is greater than 1, or they could be inverse, where the Kh upon Kd is less than 1. So मतलब directly bond breaking rate determining step में involved नहीं है. There are two cases for that. Okay, so let's talk about this. Also, they are classified as alpha or beta, normal and inverse, like that, depending on the location of isotopic substitution relative to the reaction site. I'll tell you the example कि alpha beta क्या है, ये भी discuss करेंगे. चलो. Now, first thing, this results from tightening or loosening of bonds at the transition state due to change in hybridization. This is such a beautiful example. अगर मैं आपको ऐसे बताऊं कि hybridization is changing from sp3 to sp2. Alright, so what is happening? sp3 से sp2, some hybridization is changing, and for example, this is not a hydrogen, let's say this is a Cl. Alright, in the SN1 reaction, for example, let's say SN1 reaction में क्या होता है? A carbocation forms, and the bond angle over here was 109 degree 28 minutes. You know that it is going to be more strained as compared to this one, which is 120 degree less strained. So there is relaxation from restricted to free to vibrate it becomes. So when there is a relaxation, then the CH vibrations are absolutely going to be better than the CD vibration. Okay, and that gives you a normal secondary kinetic isotope effect. Why secondary? Because a carbon hydrogen bond is not breaking directly, and still there is an isotope effect because of the relaxation in geometry. The CH vibrations are becoming even more better than the CD vibrations. Okay, so this is the secondary kinetic isotopic effect. Alright, and what kind of effect are these, alpha or beta? Since the carbocation, since we are talking about these hydrogens which are directly connected to the carbocation, which is the reaction site, so we call it alpha normal secondary isotope effect. Okay, so the Kh upon Kd is going to be greater than 1, so it's a normal kinetic isotope effect. Now guys, look at this slide. In here we see that isotopic effects, all right, which is the inverse isotope effect, that is going to take place when we are just doing the reverse of the normal kinetic isotope effect. That is, we have gone from sp3 to sp2 because there was a relaxation in geometry and the bond angle has now increased, so the CH bond becomes better than the CD while the vibration is taking place. But here if we just do the reverse, for example sp2 से sp3 में अगर चले जाएं तो then there is going to be restricted rotation, restricted vibration. So when the coordination number is increased, when the coordination is increased, there is restricted vibration, and because of that we will have a inverse secondary kinetic isotope effect. So let's talk about these, some representative kinetic isotope effects. Also guys, if you want a PDF of this, I will provide this to you in the description. Look for the PDF in the description of this particular video. Okay. Okay. Now again, examples of primary kinetic isotope effects. First one you see PHCH2H plus Br minus gives you, this is a Br radical, gives you PHCH2 and HBr. So what kind of a reaction is this? This is the radical reaction, alright, and extraction of the benzylic hydrogen. But this benzylic hydrogen is going to be, we are going to check whether this is showing you a isotope effect or not. So definitely there's only one step. It's an elementary reaction, and you see that the bond breaking will be involved in the rate determining step. Okay, so this Br is going to abstract the hydrogen in this way. Absolutely, you see 4.6 is the ratio of Kh upon Kd at 77 degrees centigrade temperature. Absolutely, it means it is showing you a kinetic isotopic effect. All right, so very, very important this one. Let's move onwards to the other one. All right, to the second one. You see, now there are two hydrogens shown over here. We are checking the isotope effect for these two hydrogens, and they are the alpha hydrogens. And when we are talking about reaction with a base, they are absolutely going to form the enolate. But both of these hydrogens are absolutely symmetrical. They're both the same. They have equal possibility of elimination by a base. So this enolate formation is a one-step reaction, and you see 6.1 is the ratio of Kh upon Kd. That is absolutely there is a primary kinetic isotope effect. The hydrogen and the carbon bond breaking is there in the rate determining step, which is just a deprotonation basically. All right, right. Chalo, third one you see over here, you are having amine, which is a good leaving group. Looks like a case of elimination. Yes, now you can remove a hydrogen from this carbon or from this carbon. From both the carbons you can remove a hydrogen. Let's say we are checking for this hydrogen isotopically labeled, that is we will check the isotope effect for this one. So OH minus, eliminating, taking this proton away and doing elimination. If the carbon hydrogen bond breaking is involved in the rate determining step, then only you have a primary kinetic isotope effect, and we do have one here, which means either it is an E2 elimination reaction or it is an E1Cb elimination reaction. It cannot be E1Cb because there is no electron withdrawing group, so it is a E2 elimination reaction. That we understand by the primary kinetic isotope effect. This is a method of rate determination of reaction mechanism. Next one, look at the secondary kinetic isotope effect. That is, you are having an aldehyde, okay, paramethoxybenzaldehyde. To this, we are reacting HCN. That's going to give you a cyanohydrin without any doubt. So the Cn minus is going to attack over this carbon. So actually there is no role of this particular hydrogen over here. It's not involved in any reaction. It's not reacting. But it is still showing you some effect, that is 0.73. All right, why is that so? And do you see, guys, it is less than 1. Kh upon Kd is less than 1. Why is that so? Because it is going from sp2 hybridization to sp3. It is becoming more restricted. So this is showing you an inverse secondary isotope effect. Okay, about the fifth example, you see, now there are two benzylic hydrogens which we are looking for. We are going to check the reaction on. So what happens is you are doing a benzylic hydrolysis. That's a benzylic group CH2Cl, and you're just doing the hydrolysis. So what could be the mechanism according to you? We have 1.30 as the kinetic isotopic effect. What does that mean? That means it's a normal kinetic isotope effect, isn't it? Normal one. Right. So if it is a normal kinetic isotope effect, that means the rate determining, if we remove, for example, if we remove the Cl from here, what are you going to get? You are going to get this benzene, or let's say, let's write Ar, and then you get this carbon, 2 hydrogen. It is very relaxed now. Why it is relaxed? Because from sp3 it has become sp2. sp3, say it has gone to sp2, definitely it's going to change to sp3, but this dissociation which is involved in the rate determining step, the cleavage, it is a SN1 type reaction, isn't it, guys? it is a SN1 type reaction, and the dissociation of Cl minus टूट के जा रहा है, वही तो rate determining step है, उसी में hybridization change हो रहा है. That is why it is going to show you an isotope effect. Okay, so sp3 से sp2 hybridization change is involved in the rate determining step, और इसीलिए ये secondary isotope effect show कर रहा है. Okay, now last example, you see guys, it's just a bond, it's a concerted mechanism, तो ये एक ही step involved होगा, only one step reaction it is, which is the dissociation of an alkene. Over here you will see the bond rotation involved. All right, let's rewrite properly. So when there is only one step in the reaction, then definitely you don't have to worry about anything. You can just go on rotating the bonds in this way so that you get one bond over here. Elimination of this alkene, absolutely normal. So both of these are normal kinetic isotope effects, secondary one, and this is inverse secondary. I hope that all of these examples make sense to you. We are going to move onwards and see more examples. So in this particular slide, you see this example. Now we will check whether changing these protons and substituting them by deuterium, is it going to cause any primary or secondary isotopic effect. So what happens is, you are having a base and you want to create an alkene like this. Okay, what is the possibility? One possibility is E1 elimination and the other possibility is E2 elimination. So what is the mechanism of E1 elimination? That is, the rate determining step goes from sp3 to sp2 because it forms a carbocation, and if that is the case, we are only going to have a secondary kinetic isotope effect. Okay, in the E2 elimination, however, it's a one-step reaction, and that first step is only going to have the CH bond breaking along with the leaving group leaving. All right. So we see kinetic isotopic effect in the E2 reaction. It is seen for both the beta carbon hydrogen bond and leaving group, and for both the alpha and beta carbons. It is very important point, because in the E1 elimination, the sp3 and sp2 change is only going to give you the kinetic isotope effect on this particular carbon. There are two hydrogens which are connected, and if the Br minus is going to leave, it is only going to give you a carbocation which is affecting the alpha hydrogens, not the beta hydrogens. All right, so we don't have E1 elimination, we have E2 elimination over here. That's the important point. Okay, we have E2 elimination over here because the kinetic isotopic effect is also seen for the beta carbon hydrogen, these. Okay, so it's going to be PKIE like this, and yeah, both of them are giving you the same product, the alkene. Very, very nice example. This is how you understand what mechanism is present if we observe some change. Second example, acid catalyzed enol formation. Now when we are having the acid, see, we have just seen one of the examples, but that was base catalyzed. What about acid catalyzed? So in the presence of an H plus, carbonyl is going to grab the proton quickly and it's going to give you this intermediate. After that, the alpha hydrogen is going to fall, and the fall of alpha hydrogen is a slow step. So it is involved in the slow step. The carbon hydrogen bond breaking is involved in the slow step. That is what we want. Absolutely giving you a primary kinetic isotope effect. Third one, bromination. Now what happens is, this is your electrophilic aromatic substitution bromination, right? And what happens? The double bond is going to attack over bromine, as you know. This is in the presence of some acid, Lewis acid, like that. Right, so what happens? This kind of a sigma complex forms where there's a positive charge on the system. Now this is the slow step, and the proton removal in the next step, sorry, in this way, the proton removal minus H plus, that is a fast step actually. So when the proton is being removed in the fast step, you will not observe any kinetic effect for that. So there is no primary kinetic isotope effect shown in the bromination, that is aromatic substitution like this. All right, guys. So you look at this example over here. We have a very, very nice example to consider. In 100% H2SO4, the cyclization shown below occurs, all right. And if one of the ortho hydrogen is replaced by a deuterium, the rate of the reaction drops from 1.56 into 10 raised to minus 4 to 1.38 into 10 raised to minus 4 second inverse. All right. So this is how the change is taking place. KH and KD are given, rate constant. Calculate the kinetic isotope effect. All right. Yeah, the product from such a reaction contains 60% of the original deuterium. All right, write a mechanism for the reaction, this reaction that is consistent with both the magnitude of the kinetic isotope effect and the deuterium retention data. Okay. All right. So how are we going to deal with this question? Very, very simple. Only you have to calculate KH upon KD. That's it. So what you are going to do is, this is going to be your KH, this is going to be your KD. So just find out the ratio that is coming out to be 1.13. And you also have to, however, give a proper, mechanism to this. How do you give the mechanism? So you have this molecule, this cyclization is taking place in this way. So what can happen? The acylium ion has formed and one of the pi bonds is going to attack over here. As a result, the pi bond is going to, as a result, you're going to get a carbocation where, let's see that. There's one carbonyl over here. Now there's a hydrogen and there's a positive charge over this. And this is how you get a carbocation. Now the carbocation does not want to be alpha to this carbonyl. So what does it do? It is going to do resonance. Overall, it's going to do resonance over here within this ring. All right, and that is what it is doing, right? So yes, either this hydrogen could be a deuterium over here, or this deuterium could be present over here. What does that mean? That means either you can write this hydrogen on this side, or you can just invert the ring. You can just rotate this part of the ring, and you can also write in this way, that you wrote the hydrogen here because this carbon bond is rotatable. All right. And let's say the attack has taken place from the double bond close to your deuterium. Then you get the positive charge over here and resonance into the ring like this. So these are two different possibilities, right? When the deuterium is going to fall like this, all right, when the deuterium is going to fall into the carbonyl, just like a E1CB mechanism, into the carbonyl, and then when the carbonyl falls back, the double bond is going to shift over here. You get a double bond over here, this one. So this is going to be a KD reaction, and when the proton falls up like this, it's going to be a KH reaction. So definitely the KH reaction is faster. All right. The observed kinetic isotope effect is 1.13, which is a normal but secondary kind of a kinetic isotope effect. Okay, let's see. The fact that 60% of the deuterium is retained gives the KH upon KD as 1.5, that is a bit higher than 1.13. Because now for this particular question, it has been asked in CSIR Net September 2022, very recent question. For a CH bond with stretching frequency 3000 centimeter inverse, what is the expected deuterium kinetic isotope effect? KH upon KD value at 298 Kelvin for a full bond homolysis. That is, a bond is breaking homolytically, and what is going to be the effect? So this is basically the mathematical treatment of what we have been doing, KH upon KD, not just kinetically. So you look at this formula over here. This is the exact formula to find out the kinetic isotope effect. KH upon KD is going to be e to the power Planck's constant multiplied by speed of light in centimeter per second. Stretching frequency of CH bond breaking minus CD bond breaking divide by 2 KT, that is the Boltzmann constant. So if you find out the value for this, you're going to get the answer. All right, so we put in the values. This is going to be your Planck's constant, 6.63 into 10 raised to minus 34, multiplied by speed of light, 3 into 10 raised to 10 centimeter per second. All right, because the wavelengths are in centimeter inverse, and it is mentioned the CH bond breaking is mentioned 3000. Okay, you have to find out the kinetic isotope effect. Okay, so what do we see? Minus new CD. Now guys, you already know the formula. How are you going to find this? ये कहाँ से आया इतना? ठीक है, you know it already that when we are talking about the reduced mass, the stretching frequency is proportional to 1 upon under root of the reduced mass. This we are getting from the Hooke's law. Okay, so we see that if we have to find out CD, this upon this, we are going to write this is equals to under root of reduced mass of CH upon reduced mass of CD. So you roughly consider the reduced mass of deuterium to be twice that of hydrogen, and for C it's going to be the same. So how do you find this out? Let me just expand on this thing. Okay, so nu CD upon nu CH, this is going to be equals to, what is the mass of a carbon? Let's say it is 12. So reduced mass is going to be 12 into 1 upon 12 plus 1, divide by 12 into 2. This is for deuterium, divide by 12 plus 2. So what we are doing is we are actually cancelling out both of these, which is numerically not possible, but क्योंकि हमें approximation लेके ही चलना पड़ेगा, so we cancel out both of these things, 12 plus 1 and 12 plus 2. So it's going to be 1 upon under root of 2. So what we do is we are just going to multiply the CH value, the stretching frequency for this, which is given to be 3000 upon root 2. So that's going to be 3000 centimeter inverse upon root 2 की value होती है 1.414. So when you do this, you're going to get this value. Okay, now put this value over here in this equation and you are going to get the KH upon KD, which comes out finally to be E to the power 2. So D is your correct option. I want you all to try this by yourself. It's a recent year question which has been asked. So another question which was asked in December 2013, ये काफी पुराना question है, but let's look at it. Deuterium kinetic isotope effect for the following reaction was found to be 4.0. Based on this information, the mechanism of the reaction is. So 4.0 Kh upon Kd, you know that this is going to be a primary kinetic isotope effect. The value is greater than 2 and less than 7. So what you do is, you see, first thing you are having this proton is going to fall from here. If it is present in the rate determining step, then only you have such a high difference. If it is not involved in the rate determining step, you have the secondary isotope effect. But it is mentioned it is a primary kinetic isotope effect, so it's going to be involved in the rate determining step. It is going to be E2. The same solution is given over here. So as I was saying, I have prepared a PDF for all of you, kind of a notes which you can refer for this particular small topic. So I will be providing you the PDF in the description of this particular video. And guys, this was the last question that we have discussed today. I hope that you are liking this content. If you are, then please give a thumbs up. Please also share it with your friends. And also, if you want to join me on Unacademy, don't forget to use my code JAGRITI-S, and you can join me on Unacademy for complete detailed discussion for CSIR net preparation. So I'm going to see you all soon. Bye everyone. Have a very nice day. I hope this was useful. Bye guys. I will see you soon.